All right. Okay. So in this lecture, in next to, I think 90 minutes, right? We're going to talk about application under sequential ignorability. I'm going to talk about three methods: marginal structural models, panel matching, and trajectory balancing. And then we're going to talk about hybrid methods like augmented synthetic control and synthetic difference indifference. Application under sequential ignorability. You still remember this figure. Two fixed facts require strong identification assumptions. The strict exogeneity incorporates no time range confounder, no carryover effect, no feedback. And I think the most important thing is no feedback. In reality, the more likely scenario with panel data is actually under sequential ignorability. So in this figure, this is adapted from Matt and Adam's paper in APSR 2018. So here, the treatment is X, right? I'm using the X notation because in the figure X is a treatment. The outcome is Y, and Z is a covariate. However, the covariate is also time varying. It's not 100% exogenous. It may also be affected by the treatment. And I think this is a more realistic case. A lot of covariates that we control for in our panel methods are actually also affected by the treatment. So we have a contemporaneous effect from X to Y. So here, so from XT minus 1 to YT, that is the one lagged effect. And then through the other two are through ZT. One is XT minus 1 to ZT to YT. So this is another route. Okay. And then another route is through YT minus 1 ZT to YT. This is another route. All these effects are the lagged effects of X on Y. Right. So, but if we only focus on XT to YT, we may be underestimating the treatment effects, because treatment effects may takes time to present itself. If we focus on this one, and may also go through intermediate variables like ZT or YT minus 1. MSM, marginal structural model, is trying to account for not only the contemporaneous effects, but also the lagged effects. And to just a quick review on the two identification regimes, the two types of identification assumptions. One is strict exogeneity, which roughly corresponds to baseline randomization. So why the potential outcomes are independent of the treatment in almost all S, right? Any S, any T, any time, conditional on DIT and UIT. And UIT needs to be extractable, can be learned from data. I say roughly because sometimes you can also conditional on the past treatment. Sometimes the treatment sum you can also conditional on past treatment. That is fine. Estimators include, these are the estimators, right? These are not a design. These are the algorithm that we use to estimate the estimate. Difference in difference to fixed effect, the IDM, factor augmented models, and synthetic control method. I think the synthetic control method, this is my interpretation. I think synthetic control method does not allow feedback. And then we have the sequential ignorability, which corresponds to sequentially randomized experiments. You can conditional on the entire past treatment history, and then you can conditional on the history of past outcomes. But you do not, there's no UIT that you can conditional. You cannot conditional on either time fixed effect, additive fixed effects, or interactive fixed effects. You take one of them. And the methods include marginal structural models, panel matching, trajectory balancing. I put a star here because you can use trajectory balancing under strict exogeneity. This is basically an algorithm, but I would be more comfortable if you use this under sequential ignorability. Okay, first let's discuss marginal structural model. The motivation is that if we believe this model is correct, and then we have this treatment assignment process, this DAG, this is a DAG. And then if we're not talking about the model is misspecified, is heterogeneous or not, we assume this model is correct, but we cannot, if we estimate this model, beta 1 will be consistent, this is fine, but beta 2 will be inconsistent. The reason why beta 2 will be inconsistent is because ZIT is post-treatment, right? So if you can look at this graph, XT minus 1, XIT minus 1, through DIT affect YT. If you conditional on ZT, the post-treatment variable, the effect of XT minus 1 will be attenuated, because you condition on a post-treatment variable. Does that make sense? Okay. But XIT is fine because you want to estimate SIT, and you block xt minus 1, you block ZIT, and that is all you need, right? There's no additional leakage from XIT to YT, so that is fine. So beta 1 is consistently estimated, beta 2 is not. The basic idea of MSM is to model the treatment history and flexibly estimate the relationship between between X and Y. This is okay. Okay. So what does it mean by marginal? Because it's the original goal is to compare the average outcome of different treatment history, but because this confounding issue caused by ZT and also maybe past treatment, we need to look at each period of the treatment separately. So we just need to marginalize based on XT, and then integrate the ZT and the YT minus 1 out. So we look at what is the effect of YT minus 1, also XT minus 1 on Y. We look at what's the effect of XT on YT marginally. That is why why the authors call it the marginal structural effects. Okay, so our goal is to estimate this quantity tau, which is a comparison of two treatment history. One is so the X represent the treatment from time 1 to T, and then X apostrophe 1 to T is alternative treatment history. So we want to, if we have enough data, we look at what's the outcome under this trajectory and what's the outcome under this treatment trajectory, and we take an average. That is fine. But the problem is that under sequential ignorability, the history will also be affected by post-treatment variables. The strategy is to, of course, we want to flexibly estimate each term on average, maybe a flexible G function. The challenge is that the relationship between XIT and history, so YT, and the history of XIT is confounded by time-varying confounders and past outcomes. Solution proposed by Jamie Robbins and co-authors and introduced by Blackwell and Gling is to use IPW reweighting, so inverse propensity score weighting, to balance out the influence of ZIT and past outcomes. So they build so you run a logit of the treatment status, and based on past information, and then you get a weight, and then you reweight the treatment status, and then you reweight based on the treatment status, and then you get a reweighted average for this particular history, and then that will be a consistent estimate for the expected value of YIT under this particular treatment history. So limitations, it may be quite obvious to you that involves many modeling choices. What variables enter the model, and you have unstable weights if you use a logit, and then the data are very imbalanced. There are only a small number are treated, a very large number are untreated, and especially with modeling, right? What kind of interactions do you want to put in the model, and how many lags do you want to put in the model, so on and so forth. Under sequential ignorability, you cannot add a fixed effect. That's just the conventional nickel bias thing. Okay, so the next method is panel matching. A lot of you must be familiar with this method. Gets more and more popular, and for good. I really like this method. It's also based on sequential ignorability. My interpretation, essentially, past info can affect today's treatment assignment. No cross-sectional spillover, allow limited carryover. The S amount is this one is the average treatment effect policy change for the treated. So this F is a few periods. So F can be 0, 1, 2, 3, 4. There's a few periods looking into the future, and then you're comparing. I'm sorry, this is error. This T minus 1, T minus 1. You're comparing units that remain. It's just like DIDM, very similar to DIDM, right? Looking at joiners and then looking at their stable comparisons, and then you conditional on past treatment history. You look at the effects on those whose treatment status have changed. Does that make sense? So I think this is a less ambitious goal to MCM because it's focused on switches only, and force the remainders of the treatment history to be the same or relevant. You first narrow your focus to comparisons in which the treatment history, at least for a couple of periods in the past, are exactly the same. And then you compare units that just have changed its treatment status and a unit that have not changed its treatment status. So I think it's less ambitious, but maybe you can get more precise estimates than MCM because it's non-parametric, or at least semi-parametric. So the procedure, it creates a match set for each transition based on treatment history. You want to make sure that treatment history is not the same. And then you refine the match set by any matching or weighting method. The others in the paper mentioned Marginal distance matching, propensity score matching, or weighting, and of course other methods are can be used. And then you compute the ATT using the refined set. And then you calculate standard errors using block bootstrapping or theoretical approximation. So let's say this is the example of democracy, the Asimoglu's paper, and Causal paper, the effect of democracy on economic growth. So let's say if we focus on this country, right, and then this country becomes democracy in 1991, maybe an East European country, and you want to compare it with units like these units that are not treated up to 1990 and then remain. These are autocracies, remain autocracies at least until 1990, and then stay autocracy at least for one more year. So these can be the control for this guy. So let's say, so here is another example by the author. So if you look at Thailand gets treated in 1978, becomes democratized, and then Argentina can be in the match set for Thailand because the treatment history up to 1977 is exactly the same, and then one switch to democracy, one remains autocracy. And then you also matched on a few other covariates. So this is a demonstration. Before refinement is essentially these countries are of similar treatment history, and then you match on the past outcome and also a bunch of covariates using different methods. Marginal matching, propensity score matching, propensity score weighting, and then you look at the relationship between treat and control there, especially with propensity score weighting, which you have more room for a perfect match. The treatment and the control look more alike. Okay, and then if you use this method and then look at the treatment effects a few periods into the treatment, what you can see is that transiting to democracy does not have a positive effect or statistically significant positive effect, but exiting a democracy has a negative effect. Okay, so actually, I apologize, I slightly misrepresent the method. The authors does not assume sequential ignorability; they assume sequential exogeneity. So I explain what that means instead of sequential ignorability, and use the difference in difference to estimate the ATT. And so what does that mean? It means the error term is conditional on past treatment, and then a bunch of past information, including past covariates and outcome, and then unit fixed effect, and then time fixed effects. Once you condition all of them, it goes to the expected value of the residual is 0. This assumption implies parallel trends after conditioning on this bunch of things. Note that this assumption embeds functional form requirements. With sequential ignorability, you actually do not require functional form assumptions. The methods you use to do the matching or weighting will require functional form. What kind of features enter the matching or weighting? But sequential ignorability itself does not require functional form. But if you have a model like this, you have a unit fixed effects. As we discussed earlier, you are implicitly introducing functional form assumption. Here, one of the functional form that can satisfy this requirement is this model with additive fixed effects and then with some lag terms. And the other find out a way to consistently estimate the treatment effects beta without nickel bias, I think. But I don't know. The question I have is I don't know how specific and demanding these assumptions need to be. If I were the author, I would probably not go the DID route. Simply after conditional on past information, just using difference in means estimator. This is, I think, from a design perspective, cleaner than combining difference in difference with sequential ignorability. And I think the author do this because after matching, because limited data, after matching, there are still some biases remain, and that they want to use the difference in difference estimator to take out the bias, especially the level difference. between the treated unit and matched control unit. I think that's the motivation. That can be problematic. I don't think that's a big practical issue. Practically, it should work, but there has been theoretical discussion based on simulation to show conditional on past outcome in a DID setting can lead to biases if transitory shocks are important parts of the outcome. Meaning what? Meaning if you condition on the past outcome, but you have some biases remain. You have some imbalances remain, and if these imbalances are actually caused by transitory shocks or random shocks, some happen to have a bigger y(t-1), some happen to have a smaller y(t-1), and you subtract using a DID, subtract that previous period, you actually result in bias. So that is if your functional form assumption is incorrect. So that is a potential caveat, but I understand why the authors do that. But if I still understand this paper as a paper under sequential ignorability, everything works very neat. You don't have to worry too much about its functional form. Okay, so pros and cons. It requires sequential ignorability or exogeneity instead of strict exogeneity. I think that's one step further. And allow treatment reversal and limited carryover, another relaxation of the assumptions required by two fixed effects. And it has weaker functional form assumption. It allows a variety of matching and reweighting methods. It has also limitations. One is arguably narrow focus on the estimate, and lots of data are chopped. That is actually, I think, the one limitation of this method, because it chops data into small parts, and you basically lose the temporal spatial structure of panel data, which may allow you to extract more information. That is one potential limitation. And normally imbalances remain, and then you have to appeal to a functional form assumption, use a difference in difference approach to address those imbalances. And there are many choices require user discretion. What kind of features enter into matching, how many periods you want to condition on, things like that. So we talk about MSM, we talk about panel matching. Next, I want to talk about sequential balancing approach under ignorability, under sequential ignorability. So we briefly talk about the balancing algorithm for the SCM, synthetic control method, in lecture 2. But an algorithm can be used in a different treatment assignment mechanism and different designs. An algorithm is just a machine, a function. What assumption you want it to operate under is your choice. Under sequential ignorability, so let's say the treatment assignment for IT is a orthogonal to potential outcomes under IT, conditional on or past covariates and or treatment history and or past outcome. And then we want to balance on all these things. We use VIT to denote all this past information. The challenge is that we don't know the exact functional form of this quantity, right? The VIT can be fairly complex, and we also don't know the outcome model exactly. Note that there's no fixed effects, okay? No additive of individual fixed effects because we are under sequential ignorability. In other words, weights can achieve mean balance. If we achieve balance for the level terms, may leave treated and treated different on nonlinear functions of VIT. So we talk about Robbins et al. In JASA, in which they introduced a mean balancing approach for synthetic control. So here, this is a paper by me and Chad Heslip at UCLA. We extend this to balancing on higher order terms using this kernel function phi. This kernel function will lift the dimensionality from P to P+. P+ arguably is much bigger than P in a kernel space. And then once we match on the kernel, roughly speaking, the entire distribution, the joint distribution of V, you can understand this V, I'm writing Y pre, but Y pre is part of V, is balanced between treat and control groups. So in practice, we seek approximate balance. We work from the largest principal components of this product matrix, and then to see how much progress we can make. So we choose the Gaussian kernel, and I don't have time to discuss this, but there are some implementation issues, how we form the kernel, so on and so forth. The kernel matrix will be n by n. So n being the sample size, the number of treated units combined with the number of control units. So it's a large matrix. One limitation of the kernel method is that we need a lot of computational power. The computational time is of the square term of the number of units. The trajectory balancing, we call it trajectory balancing because it gets the entire joint distribution of pre-treatment outcome as similar as possible between treated and control units. instead of just getting the mean right. So you can understand this as balancing on higher order features, such as variance, curvatures, the shape of the curve, and so on and so forth. So it tries to balance on the multivariate distribution of VI, of all the pre-treatment information. And this can matter when you have nonlinear functions as confounders, especially when the pre-treatment period is short. I'll give you one simulated example. Let's say in the data you have 200 countries driven by 2 different types of GDP. One type of economy grows at 3% annually, like the US, fairly stable economy. Another type of economies are very volatile, follow this sine cosine functions. If you look at data, you have the control. For the treated data, you only have those stable, steadily growing countries. For the controls, it's a mixture of 2 distributions. If you use mean balancing, you will have almost perfect balancing, but the green lines show you the heavily weighted control units. With kernel balancing, you would find basically the type of DGP that is similar to the type of DGP in the treated unit. So it will not only balance on the means, not only gets the means right, but also will get the distribution of the trajectory right. And it works better when compared with the mean balancing when the number of pre-treatment periods is small. Like here, you only matched on 2 pre-treatment periods. The kernel balancing, which is the black represented by the black dashed line, is already doing pretty well, while the blue line, which is mean balancing, does not do very well. And the red one is the correct answer. As you have more and more pre-treatment periods, mean balancing start to do better and better, because in order to achieve mean balancing, you also need the data to be more like when you have more time periods. When up to 10 pre-treatment periods, these 2 methods are fairly close. Here is a figure to show what kind of information is encoded in the kernel matrix. The x-axis is the log variance of the pre-treatment outcome. The y-axis is the first principal component of the kernel matrix. And as you can see, the treated unit all have pretty low principal components of the K, and the variance is also pretty low. The variance for the red dots are pretty low. And then if you use kernel balancing, the controls that have heavy weights also have pretty low variance. The slowly growing economies have pretty low variance, while those volatile economies have larger variance. And if you match on the kernel matrix, it will give more weights to the type of data that is more similar, that are more similar to the treated units. To see this in action, we look at the effect of having a seat in China's People's Congress on firms' return. This is a classical event study. You look at a person taking a seat, taking a political position in the parliament, and see whether that position gives your firm additional benefit. There are 48 treated firms, close to 1,000 controls. If you use synthetic control, it's going to take forever. If you use the balancing approach, it's actually much faster. 3 pre-treatment periods, 3 post-treatment period, and then 2 covariates, state ownership and revenue in 2007. And then we try to balance on both the covariates and also the pre-treatment periods, and also the higher order terms using a kernel transformation. So this is the distribution of the treated data, the trajectory of the treated data for the 48 firms. And this is, if you use mean balancing, the mean will get exactly right, but the distribution of the trajectories are not exactly the same as the treated. But if you use kernel balancing, they look almost exactly the same, because kernel method tried to get the distribution right. And if you use this is unweighted, if you look at the mean balancing gets the mean exactly right for the variables entering to the balancing scheme. For the kernel balancing, it gets almost exactly right with some imbalance remain, because they try to work harder on higher order terms. But if you look at the variance, it actually gets the variance almost exactly right, while mean balancing doesn't care about higher order features. The effects are not that different. If you use kernel method, the effect is more conservative, but we can actually use the kernel method to study distribution effects like quantile effects, because now you get the 2 distributions almost exactly the same. Okay, to summarize, removing time invariant confounders like additive fixed effect is constant. In order to do that, you have to assume there's no feedback, which is implied by the strict exogeneity assumption. Sequential ignorability may be more desirable than strict exogeneity in many applied settings, because you can actually tolerate more complex DAG. And both MCM and other panel non-parametric or semi-parametrics are repeating. MSM, marginal structural models right now still require fairly strong functional form assumptions for both modeling the treatment assignment and modeling the outcome, but these assumptions can be relaxed. Other balancing matching approaches are repeating, but so far, right now, they're only applicable to a small number of user cases like a staggered option, or you have to drop a lot of data. They're kind of data hungry. The things will quickly get more complex when the number of treatment history grows, as we have seen again and again. Inference is hard with a small number of treated units under sequential ignorability as well. Okay, so next, after a 5-minute break, I'll come back and discuss hybrid methods, which combine balancing and outcome modeling. Okay, so far, we've surveyed two groups of estimators. One constructing, no matter which identification assumption or types of identification assumptions you like. From an estimator point of view, we reviewed the two types of methods. One is to construct weight balancing weights or using matching. Matching and balancing, I see them as very closely related because matching is a special case of weighting. You give 0 weight to some units and one to other units. And another method is, another group of methods is basically modeling the conditional outcome using what information in your hand. And combining this approach will likely produce doubly robust estimator. This is fairly not surprising to those of you who are familiar with doubly robust estimators. And some methods, as we discussed, include semi-parametric differences, semi-parametric DID, panel matching, trajectory balancing. Are already doing a simple version of it. They do the balancing, they do the regression. They try to get advantage from both worlds, but there may be some costs. But we can do it more systematically. So I will review two new methods, mostly the first one, and then quickly go over the second one that formally adopt this idea. So the first one is augmented synthetic control, or AugSynth. The package is pretty well maintained. And another one is synthetic control, synthetic difference in difference. There are a lot of names out there, but as long as you understand what they're doing, that's fine. So the two approaches differ in the order of doing weighting or modeling. With augmented synthetic control, you do the modeling first, and then weight based on the residuals. And with synthetic difference in difference, you weight first, and then put the weight in a difference in difference estimation. Okay, so with augmented synthetic control, again, notation, we assume unit 1 is being treated. It can accommodate actually more than one unit, doesn't matter. But for simplicity, let's assume one unit is treated. And then there are a bunch of pre-treatment covariates. The basic idea is that you run an outcome model, you run rich, you run counterfactual estimators, and then you obtain a model fit denoted by MXI. XI are the covariates, M hat XI. And then you balance on the residuals, obtaining weights, gamma I hat. Those weights are obtained using the residuals, okay, not using the original data. So the treated average is constructed using the following equation. This is the first part is what is analogous to synthetic control. You have the weight, you put weight on the outcome for the controls, and then there's a bias correction part, which is the difference between the estimated outcome model and the reweighted average of the expected Y. So we use this part to debias. So if you are familiar with matching, debias algorithm in matching, I think it's by Inference and Causal, right? You're essentially using a regression to deal with the remaining imbalance in the covariates. This is a very similar idea. So you can rearrange the term to get this equation. The second equation is a re-expression. So the first part is your outcome model. You use your outcome model to predict your counterfactual outcome. This is very much like what we discussed, the counterfactual approach. And then we also have additional approach to address the remaining residual imbalance. So this is the difference between between my outcome for the control and then my predicted outcome. So how much remains, how well this model does, and then I want to adjust by the weights. These are two ways to understand this method. Okay, so the balancing weights can take care of the remaining biases from the outcome model and then the model is doubly robust. So if the model is perfect, it's almost perfect, or the expectation of the errors is 0, so this term will go to 0 by expectation, right? So we don't. So the balancing weights doesn't help much. So it will help when the model does not perform perfectly. Okay. All right. So we can do inference by either jackknife or block bootstrap. So there are several innovations with this idea. One is to simplify synthetic control method based on entropy balancing. We talk about this idea from the Robbins paper 2017. It is more computationally efficient. And also this paper shows Michael and co-author in their paper, they also show a connection between, we'll explain in the next slides, between IPW weighting and the entropy balancing approach. Essentially, the balancing weights have a IPW interpretation, which is nice. And a second innovation is that you obviously combine outcome model with balancing weights. It's flexible and to be robust. The model can be very flexible, and then you balance on the residuals to ensure if the model makes some error, you still can have a second step to deal with that. It will achieve better balance, lower bias than either the outcome model or matching alone. It also minimizes model dependency because you have a second step as a safeguard. The example the author used in the latest version of their paper, the paper has many versions. I think now it's in JASA. They use a rich augmented synthetic control method. So basically the outcome model is rich. They use a rich model as an outcome model. It has, consistent with the second point, has better balance, lower bias than either the outcome model, which is rich, and synthetic control alone. It can also be represented as a weighting estimator, which allows negative weights because of the augmentation. Again, it inherits the feature from the simplified synthetic control, which has IPW interpretation. Okay, so let me review again. Maybe some of you have forgotten because I wasn't very explicit about this earlier. So what do we mean by simplifying the synthetic control method? The original synthetic control, the objective function is a Euclidean distance or weighted Euclidean distance between the covariates entering the matching. And entropy penalized synthetic control matching, a synthetic control method by Robbins, is using the entropy of the error. It's actually, I'm sorry, this may be minus sign. The maximize the entropy, so minimize the minus entropy of the weights. So you want the weights to be as dispersed as possible, as close to uniform as possible, such that these normal conditions are met, such that the weighted covariates or predetermined outcomes included is the same as the covariates value for the treated unit, and then the weights added to 1. So the Michael and co-authors in this paper, they show that this approach, this entropy penalized synthetic control matching, synthetic control method, can be interpreted with exact balance. If the exact balance is achieved, this ensures exact balance is achieved, is a IPW with a logit link. So here in this equation, the alpha and beta are coefficients from a logit regression of D on X. X are the moment conditions. This is nice because to answer Brian's early question, to run logit, you get very unstable weights, especially you probably cannot even run with one treated unit. With one positive cases, the rest are negative, you probably cannot run a logit. But you can do balancing, and then this balancing has an interpretation of IPW. So that is very nice. So you basically circumvent the weighting problem by conducting a balancing scheme. Okay, so what is rich augmented synthetic control method? So this is a primary example you used in the paper. The outcome model is a rich model. It's a L2 regularized regression method. So the first part, the general form is the first part is the SEM. But note that this gamma hat is from balancing on the residual. Balancing on residuals. Okay, not on the original Y. And then you have a second term to debias, taking care of the remaining imbalances from the ridge regression. This is a general form with a rich regression as the outcome model. Of course, the first term is still the analogous to SEM, and the second term is what you get from ridge. Right? So this is the ridge coefficient because it's a regression, so it's x beta. Although this eta is regularized using an L2 penalty. So ridge augmented synthetic control weights can be, if you rearrange some of the terms, you get this equation. It's a summation of two terms. One is the so-called synthetic control weights. It's actually not exactly synthetic control. It's the entropy weights on the residuals from ridge, but you can sort of see this as an analogous to the original synthetic control weights. And the second part is a bias adjustment from ridge. So this first part, okay, so this is the, as you can see, for those who are familiar with ridge, so this is in the denominator, right? This is a ratio, right? It's just like ORS, and this takes care of the difference, right? If there's no imbalance remain, so this adjustment simply goes away. If you already get perfect balance, then you don't even need to have that term. If you still have some imbalance, you have a ridge adjustment, and this penalty prevents this second part to explode, because there you always have something in the denominator. Okay, so the paper shows both using simulations and in proof that if you use the augmented weights, your weight, sorry, I should have a hat here. The augmented with the augmented weights, the balance significantly improved compared with not using the outcome model. And because of the second term, the weights can be negative. Okay, these weights can be negative. It's possible, but this weights, the first weight, it must be positive because it's coming from a balancing scheme, and because of the adjustment from ridge, the weights can become positive, can become negative. But these negative weights sometimes help balance. Okay, so this is they apply this method to, again, California proposition 99. They use a deep one out jackknife to conduct inference, and this is original synthetic control. This is augmented synthetic control, and this is the augmented synthetic control plus some covariates. Because they're using the simplified entropy penalized balancing method to replace the original matching method, actually the weights are more dispersed. These brown diamonds symbols represent the weights from the augmented synthetic control, while the red-ish dots represent circles represent the original synthetic control weights. The original synthetic control weights are almost more sparse, if you remember, but the augmented synthetic control gives more dispersed weights to different units, and some of the weights are negative, right? These parts, the weights are negative. Okay, so these are for the augmented synthetic control, and then the second approach is fairly similar, synthetic difference in differences. They assume, again, we assume there's one to the unit. Here they assume unit n, not unit one, and one post-treatment period, and the weights added to one. So they add the procedure is that you first get the weights cross-sectionally, synthetic control weights for each control unit, and then you get a synthetic control weight for each period. The first is for each unit, so for each control unit, and then for each time period. I listened to a presentation by one of the authors. Actually, according to them, they think one of the innovations of this paper is they try to make synthetic control more symmetric. The original synthetic control is not symmetric. Only the weights is on the controls, not on the time periods. It's on the units, not on the time periods. They want to fix this by introducing another set of weights on the time periods. So you have lambda synthetic control weights for the time periods. You have omega synthetic control weights for the units. And then you put those weights on, this observation is on T by N, right? T by N. You put those weights on both the time dimension and the unit dimension, and then reweight a difference in difference method. They show that if the weights, either the weights are correctly constructed or the difference in difference method is reasonable, you get a deeply robust estimate. Either the synthetic control weights or the outcome model is correct, the causal effect will be identified. Of course, this this model can be more complex, can be more complex than a DID model. All right, so I think we finished inferences by jackknife. Okay. So what we have learned during the past, the identification assumptions required by DID are not necessarily weak. We talk about what they imply. You need to have functional form. It is not functional form free. Although you look at the parallel trends, it looks like there's no functional form assumption, but there are actually functional form assumptions, especially additivity. And with the setup, you already ruled out feedback. Remembering difference in difference, we have two peers. When you have that problem set up, you already ruled out feedback from past outcome because the units cannot change group, right? Feedback meaning that depending on the realization of Y1, you can be of a different group in the second period. This is not allowed in difference in difference. Although when we learn difference in difference, it's not as clear, but this is actually embedded in a difference in difference design. And of course, SUVA assumption for difference in difference requires that there's no spillover, no interference, and no general equilibrium effects. If you think about the classic seminal paper for difference in difference, we may actually be concerned about that, right? The Pennsylvania and the New Jersey restaurant, there may be people moving around, there may be general equilibrium effects as well, but these are not considered in a difference in difference design. A lot of actually in our social science settings, we may have legitimate concerns for that assumption. For example, if we allocate grants from the government, if you give more money to one locality, the likelihood of other localities getting money from the central government is lowered. But normally we don't take that into account, at least in the reduced form framework. I know some people are doing structural estimation, and two effects models are often problematic. On top of the DID concerns we just reviewed, you assume homogeneity, and failure of this assumption will lead to negative weighting. We've spent some time on this, and we also assumed either no carryover or limited carryover with parametric assumptions. So ignoring them may be problematic as well. And with counterfactual estimators, including SCM, including the G-things or matrix completion, they can be helpful, but they're not assumption free. They have functional form assumptions, or they're scale dependent, things like that. And of course, they rely on certain identification assumptions. And methods under sequential ignorability are, in my opinion, relatively underdeveloped and underutilized. Not many people, if you look at the literature, the empirical literature at least in political science, I'm quite sure in economics as well, they're not very regularly used. Partly because the procedure is fairly complicated, and then the functional form assumption is fairly strong, and also there are no well-accepted tests for the plausibility of the assumptions. Not like with the DID, at least we can do some event study type of plot. So that is, I think, why people are not using them. But I think more research needs to be devoted to that group of work. And in our discipline, Matt Blackwell has done a lot in not only introducing this idea, but also develop based on existing studies in other disciplines. And doubly robust estimators are appealing, have appealing statistical properties, but so far have relatively few user cases because you rely on balancing. Right now, what people are dealing with is synthetic control or staggered adoption. Maybe we can investigate how we can use these methods for a more general user case, like treatment reversal or things like that. And we haven't been spending much time on modeling the treatment status. There are several papers using IPW weighting to model the probability of getting treated under staggered adoption. But I think a lot of if you just look at the treatment status plot, for sure they're not randomized. They're not within unit randomized. But what is the treatment? What is the possible treatment assignment? Maybe it's duration model, maybe other types of models. But we haven't spent much time on in those areas. Okay, so what are my practical recommendations? First, you want to plot your raw data. Plotting your raw data, especially having a better understanding of your treatment status, how the treatment status is distributed, help you see some obvious problems, and also based on that, think harder on what can possibly be the treatment assignment mechanism. Although very often you still don't know by looking at the data, observational data, if you don't help collect them. But at least you need to ask yourself what you think may be the hypothetical experiment that is being run. And if you think feedback is weak, you can start from estimators that are using under parallel trends, such as DID, DIDM, counterfactual estimators, augmented synthetic control, and then find out a way to check pre-trend. This cannot directly test the parallel trend assumption, but gives you a sense to what extent they're believable. And if the feedback is pretty strong, there's all kinds of errors here and there. maybe you need to consider sequential ignorability. In some simple setting, you can use panel matching, trajectory balancing. In more complex settings, you probably need to use MSM, although right now MSM still require pretty strong functional form assumptions. Testing are very important. Whichever method you use, at least you can be very innovative. At least you need to conduct some type of placebo test to show that basically to make your assumption falsifiable, right? To check whether your identification assumptions are practically reasonable. And of course, uncertainty estimates are very important. Very few paper in our discipline, this may be a surprising fact, are using bootstrap or cluster bootstrap for panel data analysis. Although this has been in the econ literature, I think things are much better on this front. Cluster bootstrap is very widely used. It at least can avoid some problems. Again, bootstrap methods also is a asymptotic method, right? It works well with large sample, but the finite sample properties of bootstrap or jackknife are much better than asymptotic variance estimators. And this is very well known. This problem becomes especially severe when the number of treated unit is small. Like in synthetic control is very difficult, but with some intermediate case, like if you have 20% of the units are treated and you care about ATT, then the number of treated units are really important. And jackknife and cluster bootstrap are safer case in those scenarios. And what are maybe the future work? We need to rethink panel models from a design-based perspective. We just get started on that front, as you probably have observed from the lectures in the past 3 days. But there are a lot of work emerging, but I think there's a long way to go before we can fully understand what is going on from a design-based perspective with panel data. And there's a spatial dimension that is underexplored. We talk about unit dimension, time dimension, but the unit dimension very often are located spatially. If we can get micro level data that actually have such geographic or spatial information, you can do a lot with modeling because those spatial distance actually matters. My co-author Wang Ye, who's now was an NYU PhD and now at UCSD, has some quite exciting work on that front. And Luke Stanford, who was at UCSD, also he's working on remote sensoring. By design, has a spatial dimension. He's doing some really exciting work. And policy diffusion is important because that is basically policy diffusion literature is about how to model the treatment assignment, right? The treatment maybe affect each other geographically. And Naoki, I think most of us are familiar with him. All his work is making some great progress on that front. And I think these issues are related. If you have a better understanding of policy diffusion, policy being the treatment, you may have better, you may be able to do better causal inference on those policies. Very few studies are tackling continuous treatment. I didn't even mention continuous treatment in this 3 workshops because they're complicated. Because it's complicated and because people still have demand for using continuous treatment in panel data analysis. There's also some research opportunity there. And there are a lot of developments in Bayesian models. I mentioned a little bit, Gaussian process, so on and so forth. And then a lot of new developments with MSM, more are needed. And of course, the intersection between machine learning and causal inference are just getting started. And also, panel data is a place where these methods can be used, just as we have seen with matrix completion. But I'm quite sure there are more methods that can be used in the panel setting. Up to write some packages with my collaborators, PanelView, GSync, SPECT. I try to combine GSync, SPECT because I think these are similar things. And trajectory balancing is still at the alpha stage, very early stage. And there are a couple of very useful and more packages out there. LFE package is very useful for any panel fixed value estimation. The analogous package in Stata is RAG-HDFE, right? For those who don't know, I'm quite sure economists love it. It's pretty well maintained. And panel matching by Yiqing Xu and Eric Wang. It's also pretty useful. This paper is AJPS forthcoming, I think. And synthetic control, this synthetic control package, of course, is very useful. Augmented synthetic control is also pretty well maintained by Ben Michael and co-authors. And yeah, that's it. All right, so maybe let's call it a day. Thank you so much. And please, for those from WashU, please sign up for office hours. Let's chat in a one-on-one. And also, of course, Stanford students, feel free to talk to me. And other participants, I really like to thank you for your enthusiasm. I know some of you are from a different time zone. Thank you so much. I will maybe post it on, after some editing, you post it somewhere, the videos, to have some positive spillover. And feel free to email me if you want to talk to me. Thank you so much. Bye-bye. Take care.